They're organized in the, like I say, in the McDonald laboratory there. So 3 of us are theorists, and the rest are experimentalists. And we have, of course, a strong contingent of students from the lab here, whom many of you might have met also. Before I get started, though, I want to repeat something I heard a couple times yesterday, that this is a lecture, not a talk. So let's have a discussion, okay? If I don't get through all my slides, I'm not upset, it's okay. So stop me, slow me down, ask me questions, raise your hand, you know, that sort of thing. I really want you guys to take something away from it. I'm not trying to impress you with all my stuff, so like I say, if we don't get through it all, it's okay. Also, and I apologize if you guys did this before, but I know some of you actually aren't from strong field physics background, so if you aren't, can you just raise your hand? Okay. So that's a few of you. So feel free, you guys should feel free also to ask questions. I'm hopefully pitching this at a level that everybody will benefit from. Now, what I'm going to talk about, and it's in a little bit different order than I told Hossein, so, but I thought this order might fit better with what other folks have talked about. And what I'm going to talk about is strong field multicolor coherent control. Now, those words sound a little bit different than what people have been talking about, but I'll show you it's really the same stuff. And my subtitle is Putting the Photons Back in Strong Field Physics. We've heard a lot about, we've heard a lot about 3-step models in the field and trajectories. You won't hear any of that in my talk, okay? I'm a theorist, I should have mentioned that probably. I'm a theorist. I like quantum mechanics, so I look for quantum mechanical explanations of things, not classical, okay? I want to get to the point where the simple interpretation is the quantum mechanical one, not the classical one, okay? Because I think when we get to that point, then we're going to start being able to use quantum mechanics to do things that we want. When that becomes our intuition, we'll be able to use it and manipulate it and all of those things much more effectively, okay? That's just my personal bias. So, I like to start with this, especially like in colloquia, because that usually gets people's attention, right? Einstein was wrong. What the heck do I mean by that? Well, Einstein, of course, told us about the photoelectric effect, and when you shine light on matter, you get electrons out. We all learned this in our, I don't know, beginning physics. We call it modern physics in most US curricula. And what you typically learn in the textbook, and I don't know if Einstein actually said it this way, because I didn't read his original paper, but what we learned in the photoelectric effect, the energy of the electron is the energy of the photon minus the work function, the ionization potential. We also learned that that energy does not depend on the intensity of the light. Moreover, there is a minimum frequency for that light coming in, okay? Because if h bar omega is not bigger than phi, then the work function, the ionization potential, you aren't going to get any electrons out. Well, I imagine by now, having heard many talks already, that you understand that that's not exactly true, okay? These are spectra, ATI spectra, meaning photoelectron spectra by shining strong lasers on an atom. I don't remember which one this is, argon maybe. This is from Gerhard Paulus from many years ago. And you can see all of these peaks, of course, are the ATI peaks. They're separated by 1 photon's worth of energy. So you absorb the right number of photons to get into continuum, then you keep absorbing photons, okay? Well, that sort of puts the lie to this photoelectric effect, at least as stated this way. This is a 1 photon effect, that's the key point. This is 1 photon, these are many photons. So in that case, we should modify all the rules for the photoelectric effect, that the energies actually can be obtained, the energy of the free electron can be had from absorption of many photons, okay? And that the energy does not exactly depend on the intensity of the light, okay? Or it does depend on the intensity of the light. And that there's not a minimum omega, because you can absorb 3 photons, or 10, or 50 in principle, and still get electrons out, okay? So that's the difference between, and we've heard it many times already, between sort of standard photoabsorption spectroscopy traditionally done for decades, and the multi-photon sort of effects that we're talking about in strong field. Okay? Now, you don't just see these photon peaks in single fragmentation and simple ionization. What I'm showing here are some pictures from a paper that I wrote a while ago with Lars and one of his students and one of my students for ionization, in fact, dissociative ionization of H2+. So you take H2+ and you shine a strong field on it, and you break it into all its pieces. Okay? And what we learn is that the same sort of energy conservation expression still applies. That all the relative energy finally, between all these fragments, has to be the energy of all the photons absorbed minus whatever the initial energy was. Okay? And that means that if you plot the joint energy spectrum as a function of the electron energy and the relative nuclear energy, you get these lines. Okay? Those lines are the multi-photon lines. So the system absorbs 15 photons, and that energy gets shared between the electron going away and the nuclei going away. Okay? But there's still only so much energy available, and that's the energy given by energy conservation. So that same sort of multi-photon effect we saw in ATI applies when you have more particles in the final state. Okay? And that's, because it's just simple energy conservation, you can see that's nothing particularly special to this system or any system in particular. Okay? This energy conservation idea is going to work in essentially all cases, no matter how many particles you have in the final state. Okay? Now, whether you see these peaks or not depends somewhat on the details of the pulse itself, of the laser pulse. Okay? But we can talk about that a little later. But again, this I should have mentioned. These are calculations. These are theory that we did. And then Reinhard Werner, oh yeah, here it is, did an experiment. Now, he didn't do the experiment corresponding exactly to the calculation we did. He did H2 plus a strong field and measured the outgoing hydrogen atoms, neutral, a proton and an electron. Okay? But that's still 3 particles in the final state. And I said it's only energy conservation, so it doesn't really matter what those 3 particles are. If you measure all their energy and you plot it, you're going to see these multi-photon peaks. And so the experiment saw exactly that. Okay? And we expect to see that essentially in any system. Okay? So the thing that I like to think about these kinds of plots is they give us a natural way to look at more complicated systems, because this line is a line of fixed total energy. So if you look along this line and see where the maxima is, that tells you how the energy was shared between, say, the electrons and the nuclei. So in this case, this is the nuclear axis, H plus H plus. In other words, hydrogen plus proton. Okay? And this is the electron axis. So this says the peak is closer to this side, so the electron energy was low, and, well, the scales are different, so that's actually about 2 eV and that's about 2 eV. So they both took away about the same amount of energy. Okay? But what I'd really like to see, and this is the coherent control aspect, is can we move that blob around? Can we force the electron to take away more energy? Okay? Can we force the electron, nuclei to take away 0, the electron to take away 0? That's the coherent control aspect. Can we manipulate the system at a quantum mechanical level by shining the light on it? Okay? And that's, of course, not just our goal. That's the goal of basically everybody who's talked here when they've talked about 2-color kinds of processes to manipulate harmonic generation, to manipulate whatever it was. That's coherent control. You're trying to adjust the light to get an outcome that you want. Okay? So typically when people talk about the harmonic generation and things like that, they don't call it coherent control. Coherent control is language that comes more from, say, the chemistry side, and controlling things like the nuclear motion, chemical reactions. Okay? And it's coherent control, and maybe that's my next slide. Let me just go here. It's coherent control because it's fundamentally a quantum mechanical thing. So the coherent means quantum mechanical. That's what they're really implying with that statement. And the idea is that you just want to set up the Young's double slit experiment. Okay? You want to have 2 or more pathways, and you want to, control the relative phase between them. So we know the classical, everybody I think knows the classical Young's double slit. You have a light source, you have 2 pinholes, that provides 2 different pathways over to your screen, and you see this interference pattern over there. And that interference pattern, of course, is controlled by the relative phase along those 2 paths. And as you scan that point along here, that phase difference will change. Okay? And that's what gives you the interference. And it looks more or less like a cosine or sine squared of the phase difference. Okay? In a quantum system, we have exactly the same thing. So you start from, let's imagine in this case, say an atomic problem. You have one bound state energy level and another bound state energy level. Let's say that you go from this state to that state with 1 photon, or you go from there to there with 3 photons. Okay? That's 2 different pathways now. And so those pathways can interfere, and if you can control the phase of those pathways, then you can control how much gets to the excited state. Okay? So the probability to be in that excited state is the amplitude for pathway 1. So this is the amplitude in the phase for that pathway. Amplitude in phase for the pathway 2. And of course the probability is the coherent square of those things. Okay? Yeah?
Why does it, in your graph, it looks like phi 1 equals phi 2?
Which one? This one or that one?
Well, the blue arrow is the sum of the 3 red arrows.
But that's just the energy. That's not the phase.
Okay.
So we need them to go to the same state, so they have to have the same energy. Because how do you get interference? You have to have 2 indistinguishable ways to go from the initial state to the final state. And the final state has to be the same. Otherwise you don't get interference. Okay? So the energies have to match, and that's the key. That is a good point. But the phase for that amplitude doesn't have to be the same. Okay? And so we have these 2 pathways. We have a probability that looks like that. And of course you expand it, and you get the interference term. Okay? And by the way, this is classic Brummer-Shapiro control. Okay? In the coherent control community, that's the names usually attached to this idea. Now, I didn't actually randomly choose 1 and 3 photons either, because if this is an atom, for instance, then these states have parity. Okay? And so to go to the same final state, dipole selection rules apply. And we know that if we start, let's say, in the ground state, even parity, for instance, we absorb 1 photon. What's the parity of the final state? Odd. Okay? So if I'm going to go there with 1 photon, that has to be an odd state. So how many photons, if I'm going to go with more than 1, can I get to the same state with 2 photons?
No.
Because that's even parity, right? So I have to have 3. 3 is the minimum that I can have to get to the same state. Okay? Now, this expression, it's quantum mechanics, it's wave phenomena. Okay? But it also tells you, in a sense, and I'll preempt Paul a little bit, the answer for, can you measure the wave function? Well, that amplitude is effectively the wave function. Okay? Amplitude and phase together is really the wave function. Okay? So probabilities are what you can measure. Okay? So maybe I won't give my answer yet, I'll leave Paul's question intact, but to give you guys maybe a little bit more of a hint, that's what you can measure probabilities, so it looks like that. Okay? And if that's something like a wave function, what can you measure from there? Okay? But we're going to use this a lot because this is interference. That's fundamental quantum mechanics, that's coherent control. Okay? Now if you have a system like H2+, that isn't simple 2-level system, or discrete levels, where for instance you go from a bound state to a continuum state, and I hope Born, Oppenheimer and things like that are familiar enough that this plot makes sense to you guys. This would be the ground state potential, and so bound states lie in here. For instance, that would be the energy of 1. Above this threshold, it's all continuum state. So if you make a transition up here, the molecule falls apart. Okay? So if you start in this vibrational state, we can absorb 1 photon and get up into this continuum, or we can absorb 2 photons and get up into the same continuum. Okay? Now, if they end at the same energy, right, that's important, but they have different phases along the way, then this kind of relation still holds. You still have interference, and if you were to measure the fragments, the energy of the fragments out there, whoops, let me use this one. If you were to measure the energy of the fragments out there, starting from 0 and increasing, then you would see an interference pattern, okay? That interference pattern would be controlled by the relative phase of those 2 pathways, okay? Now, I hope you're paying attention. Now I have 1 photon and 2 photons. So can they interfere? Well, if I have 1 photon, the final parity is what? If I start from even parity. It's odd, right? So what's the final parity along this pathway? Even. Can they interfere? Who says yes? Who says no? Some of you aren't voting. In this case, the answer is yes. Why? Because they're at a continuum now. So at that energy, you have both even and odd states, okay? And what you measure out here is not the parity state. You actually measure, in this case, a proton and a hydrogen atom, which ends up being a superposition of those 2. And if you superpose even and odd parity states, what you get is a state with directionality, okay? And so what this process is actually telling us is we can control the directionality of the fragments by controlling the relative phase of those 2 pathways, okay? If we had 1 photon and 3 photons, we could control the yield of the fragments this way, okay? Yeah?
Perhaps another way of saying it is that you're not measuring the parities in reference state. You're measuring the direction in which they come out.
Exactly. No, that's a good point. We're measuring direction, not parity.
Because if you could measure the parities, then they wouldn't interfere.
That's right. That's right. If you could measure parities, they would not interfere. But that's not what we measure. And we'll use that a little later on very explicitly. So, good point. So what I want to talk about, the example I'll use for strong field coherent control is the carrier envelope phase. And of course, that was one of the reasons I decided to talk about this today, was because we heard a lot about this already yesterday and a bit the day before probably. Okay? So everybody I think knows what carrier envelope phase is, but maybe for those of you not from strong field, I'll just repeat this. The idea is that when you put matter in a laser field at optical wavelengths, the only thing that matters is the electric field. The magnetic field doesn't matter, okay? For all intents and purposes. So what we always write for the laser field is just the electric field piece as an envelope times some carrier, and that phase right there is exactly the carrier envelope phase, okay? And these are just 2 plots for a 5 femtosecond and 10 femtosecond 800 nanometer laser pulse at 2 phases. And you can see in this long pulse, the 2 phases, the peak field, for instance, is more or less the same. However, in the shorter pulse, the peak field is a bit different. And this is the usual argument for why there are CE phase effects. By the way, I'll say that a lot. Carrier envelope is CE phase, okay? Why there are CE phase effects is because we're in a very nonlinear regime and the peak field strengths are different, okay? So if you change the CE phase, you get different peak field strengths, you get dependence of the nonlinear processes on the field. Okay? That's the usual explanation. And since this is a lecture and you're students, I don't want to take advantage of you. What I'm going to tell you is my way of looking at it. Okay? My way hasn't really caught on. Okay? So, I don't use the standard sort of field description. Now, you'll hear some things that are similar. Tony talks about things in a similar way, but I wouldn't say that this picture is widespread. Okay? But there's nothing wrong with it. It's exact. Okay? There's no model, there's no approximation, it's exact. Just to give you a little bit of the history, at least in terms of the molecular problem, and you can't read that, can you? Because I can't read it. In 2004, we had this paper where we actually done a calculation for CE phase effects and H2 plus dissociation. Okay? At this point, C phase effects were known, but mostly in ionization problems, ATI spectra. Garrett Paulus had done a lot of work, for instance, and seen that you could control the directionality of the electron using the CE phase. Okay? You can make it go right or left, depending on your choice. And so we wanted to look at this process, just dissociation of H2 plus into a proton plus hydrogen. Could you make the proton go right? Could you make it go left? Okay? And we saw that indeed you could, as a function of CE phase. You can see that the two channels, proton plus hydrogen or hydrogen plus proton, that means right and left, we could change over a big range. And I'll also point this out, that when we say control, all we mean is that the process depends on that parameter, right? If a process depends on a parameter, then in principle at least, you can turn it around and adjust the parameter to control and get the answer you want, okay? So these processes depended on the C phase. Now, 2 years later, the experimentalists caught up and did a measurement and saw in dissociation, strong field dissociation of D2, they saw directionality plotted using this asymmetry parameter. However, I will point out that this is actually a different process. Okay? They started from D2 neutral, we started from H2 plus. Now the D's and the H's aren't the important difference. It's the charge state that's the difference. Okay? You'll also notice that I don't show energies here, sorry. Their energies actually are much larger than what we were looking at. If you wanted to try to compare these, you should be looking down at, I think it's these energies. Okay? But because they started from a different system than we did, you're going to see slightly different answers. Okay? Now, we did a little bit more work. This was 2012. We showed how we can enhance these relatively small controls, small degrees of control, because you'll notice this asymmetry parameter, and let's just take a second to think about what that can do. This asymmetry parameter can range from -1 to +1. So if you can send everything one direction, that would be, for instance, -1, or let's see, if it's over here, it would be +1. If you could send everything the other direction, that would be -1. Okay? And that's why we use this normalized asymmetry parameter, just to tell you sort of a relative measure of how well we're doing. But you can see in this plot, this experimental plot, ranges from -0.2 to 0.2. So that's not actually a huge degree of control. Okay? And if we go back, we didn't plot asymmetries, but you can see it ranges, probably the average is about 0.12. This is a probability. So 0.06 out of 0.12, sort of 0.5-ish numbers. But here, we increased the contrast by quite a lot. Okay? And this is still for H2 plus. We just,
You say asymmetries, what is the asymmetry in?
Let me go back. So here's the process we're looking at. H2 plus, you shine a strong laser on it, it breaks apart into a proton and a hydrogen. Okay? So you can have and they can measure the fragments, and they can measure the momentum distribution of those fragments. Okay? So, you can have a certain fraction of the fragments, certain fraction of the events where the proton goes this way, which means the hydrogen goes that way. But in the other part of the events, the proton will go this way, the hydrogen will go that way. So the directionality is essentially which direction does the proton go. Okay? And so the asymmetry, too many buttons, is just measuring that difference, taking how much goes this way minus how much goes that way, dividing by the sum to normalize it. Okay? So in this example, we managed to enhance it from doing nothing to our preparation of the system by about a factor of 10, it turns out. Now, I don't want to dwell on this because I want to get to the other stuff, so let me move through that a little bit and talk about the main point here. And that is that, from our point of view, all C phase effects can be thought of as a result of interference of different end photon amplitudes. okay? So instead of thinking about the field, we're thinking about photons, okay? When you think about photons, it's in a sense a time-independent kind of a picture. It's sort of a frequency space picture rather than a time domain picture, okay? And the way this comes about, here's a couple papers if you want to read where we started with these ideas. What we want to solve is the time-dependent Schrodinger equation, okay? That's what describes all of this. Time-dependent Schrodinger equation can be described in terms of the field-free piece and a dipole interaction, okay? So this is the dipole of the system. This is just the field, okay? And here's the C phase. And the key point, the key observation, and the only observation we really need, is that this equation is periodic in phi. This Hamiltonian is periodic in phi. That means the solutions have to also be periodic in phi. However, if they're periodic in phi, we can use a Fourier series to represent that C phase dependence. So we take the exact solution and we expand it in this Fourier series, and that's exact. Okay? And that's really all there is to this. The rest of it just follows from that observation. Okay? And I want to emphasize the simplicity here. So I'm going to derive this result on the board. Okay? I'm going to derive what we need on the board. So we're starting from I ddt psi, trying to match the notation, h naught minus e naught dot d cosine omega t plus phi psi. Okay? Now we say psi is this Fourier series. Okay? And all we have to do is substitute this into there. Okay? So we have sum over n, I, e to the I n phi, ddt psi n, h naught minus, now cosine omega t plus phi is e to the I omega t plus I phi divided by 2 times sum e to the I n phi psi n. All right? Okay, so now we simplify. How do we simplify? Well, the e to the I n phis are linearly independent, right? That means the coefficient of e to the I n phi on both sides has to be the same. Okay? So all we have to do is match the coefficient, let's say, of e to the I m phi on both sides, and that will be the equation for the psi n's. Okay? So on the left, we'll have I ddt psi m, h naught psi m, minus e naught dot d over 2. Now, we have an e to the I phi and an e to the I n phi. So that's e to the I n plus 1 phi. And n plus 1 better be equal to m. So that means this is e to the I omega t psi m minus 1. Right? Plus e to the minus I omega t psi m plus 1, doing the same on the other term. Okay? So that's it. That's the equation for these amplitudes. And this is the equation that we will use to understand the rest of this. Any questions about that? Yeah?
Do you have equations for the Maxwell equations? Do you have equations for the photons, or you just?
No. Yeah. This is getting at an important equation, an important question. I said, I'm going to put the photons back in, and I've said these are photons. What in the world do I mean by photons? Okay? I don't mean that I'm going to keep track of the field in a quantized way, the laser field in a quantized way. I don't mean that. Okay? In strong field physics, when we say photons, we never mean anything like that. Okay? In strong field physics, when we say photons, we mean something that has energy h bar omega. That's it. Okay? Now, to be honest, I think there likely is a deeper connection between the CE phase here and photons, because what does this expression say? I mean, this is a Fourier transform from phi space to n